All right. Now, let me share my screen. Somehow share. And here is the screen. I minimize that guy so it goes to the top. All right. Hopefully you guys can see my screen. So we continue on module 3, the third type of structure, which is trusses. And trusses, they are common structure in bridges, in houses, like this image that you see on top left corner. It's a bridge on Fraser River, I believe. The second one, another bridge. I don't know which river or lake maybe it is. And the third image below is on a house, roofing basically. We put together links. Sometimes they're made out of aluminum or steel like this one, sometimes made out of wood. And this one probably, maybe, can you guys guess where this one is? This is me.
Somewhere close to Granville Island? Or?
That's correct, yeah. Yeah, that's correct, Mohammed. It's Granville Island. The picture is on Granville Island. This is Granville Bridge, basically, right? So trusses, again, next time you're walking around, you can see these structures a lot. It's some links, they're all welded or bolt together, all right? And our objective here in this module or in this section of the module is to find out the forces that each of these members, they are like carrying, so we can calculate the stresses and so on. If you are interested, believe it or not, there are competitions with spaghetti, making trusses with spaghetti, right? So it's not making a nice spaghetti meal, it's building a truss with spaghetti. You can, later you can Google it on YouTube, you will find nice structures that students build with spaghetti, basically. Spaghetti is a weak, very weak material, right? A stick, you can, with just a half a Newton, you can break it, but you can build a truss with a spaghetti if you do a correct design that you can see on this right image. On the this woman is hanging, I'm guessing probably something around maybe 1.5 kilogram or maybe 2 kilograms, and it is stable. The structure is still stable. Okay. So, but personally, I prefer instead of wasting the spaghetti, making a nice meal. And I'm a good cook. I'm not just a good teacher. I'm just bragging about myself. I'm also a nice cook. I'm just joking. But really, I'm a good cook. At least I can make a nice spaghetti. Maybe one day later, not now. I'll make one and we test it. Okay, so, but what is our objective in this module? First, are we going to deal with 3D trusses or 2D trusses? In real world, in practice, we live in a 3D world, and of course, everything is 3D, right? But trusses, we can simplify them to 2D because most of trusses, they are arranged in a way that we can find one truss in one plane. Like in this house at the top that you see, if I just look at one section of these basically, or one layer of these trusses, which they are parallel to each other, then I can say that all of these links, right, they are in one plane. So if I analyze just one truss in this structure, the rest basically are the same. So I can, in other words, I can simplify this to a 2D truss and solve it. The same, with the same manner in this bridge, like here you see we have this plane, and parallel to that, on the other side, we have the same things, right? So I can treat this basically 3D truss to a 2D truss. Now I got confused. I hope I'm doing it correctly. But anyway, you got the idea, right? So in other words, what we are going to be dealt with in 260 or even in future in practice is going to be more like example like the one on the right side, which like for this house, a 2D truss, and or like this bridge, a 2D truss. And our plan is we want to see when, let's say in this truss, when a truck is passing, it has a big weight. We want to find out the loads in each member of this truss, and so we can basically calculate the stresses and make sure that we pick the right material and we pick the right geometry. By geometry, I mean the right size of the truss so it doesn't fail, right? And something that distinguish basically trusses from frames is trusses all made out of two force members. Like look at this truss, for example, all of these members, they are basically two force members. Like CG is a two force member, DG is a two force member, right? All of them, they are two force members. So we don't have any three force members or any other things in a truss. Okay. And yeah, so let's then move. Any questions so far? Is it clear what we are looking after? So basically we want to find out the forces in this truss, and a truss made out of lots of links, and these links, they are all two force members. We remember from the previous lectures that the two force member has three conditions. First, the force only applies at the joint. Secondly, the members, we neglect the weight, because like in this structure, compared with the weight of this truck, maybe the weight of each link is so small we can ignore it. And yeah, there is no load also on each member. All right, so with that, let's move on. Ooh, that's a busy slide, but let's see what we want to say in this slide, okay? So again, our objective, finding the internal force in each member of a truss. Why we want to do that? Well, to compute the axial stress. Why we want to compute the axial stress? Because we want to design and optimize. Remember, we want to find out if the section, the size of each link, by size I mean if let's say these bars are like a circular bar, we want to know if this cross section is adequate to handle the stresses. And we want to optimize, and we want to sort of make sure that it doesn't fail. By failing, I mean a member breaks, okay? So we have four main assumptions. The first one, we neglect the weight of members, right? Again, that's a safe assumption to say that compared with the large weight of the whole truss and the external loads, the weight is so small for each member that we can neglect. So secondly, the connection, they are all joint. The connection, they are all joint. In practice, if you look at the image on the right side, the actual joints, in fact, they are either bolts like this one, or they weld together. So bolt or welded together, right? But for us to solve the problem, we can get a relatively good answer if we just assume that the connection is joint, something like the one on the image below, like this one, right? So that's the second assumption. So it's a joint. And for a joint, we know what are the reactions, right? We have AX and AY. So the third assumption is the forces that we apply, the external forces, they are only apply at the PEng. So like the one that I'm showing here, maybe this force is like 100 kilonewton, this force is 200 kilonewton. So you're not gonna have a truss that, let's say somebody apply load here. You're not gonna have that. And the reason is, remember that spaghetti, the truss members, they are weak. If you apply load in the middle, they're gonna bend and break. Even for like bridges, they're made out of small links. The whole truss can carry a large load, like 200, 100 kilonewton, but if you apply load in the middle, it's gonna damage the truss. So that's the third assumption. And then the last one is, based on this external load that you apply, a member, by member I mean these like links, they are either under tension or compression, right? So as we said before, let's say this link here and this one. So the loads, they are either tensional loads, like this one, or they are compressive, like this one. They are under compression. And we don't know if they are under tension or compression, but it's important for us to know. And it's complicated to figure out by just sensing if I apply this load, if a member is under tension or compression. So what we do then, we assume that all the loads, they are under tension. So we assume they are all under tension. In other words, this is gonna be our diagram. Our free body diagram is this one. But what if we are wrong? Well, we just let the math to find out, okay? That's not our job. It's the math to find out if the result we get at the end is a negative number, then it means it is compression. If it's a positive number, it means we were right in the first place and it is under tension, all right? And again, if you look at 1, 2, and 3, they implies that the members in a truss, they are all two-force members, right? So they are all two-force members, and either they are under tension or compression. There are two methods which we can solve a truss. One is method of joint, and one is method of sections, which I solve one example for each, and you're going to realize how simple it is, each of these methods. And then later you can decide for a problem which method is better to use. All right. That's it, I guess. Is there any question before I move forward? Are we good? Okay, let's then move on. But before I start solving a problem using the two methods, joint and section method, which I'm getting to that in a moment, we need to know one more thing. And this is this concept which is called zero force members, right? Sounds like a weird name, zero force member. A member has a zero force, right? Sounds like that, but what is it exactly? So let's say that we have this truss here, right? And this truss, remember in truss, it's customary to just use English alphabet to name the joint, A, B, C, and there is no particular order, C, D, E, F, G, H, I, and so on, okay? And each member, we call it by its name, like we call it AF, we call member FD. That's one thing. So, and let's say in this truss, we put it on two sides of maybe on a river or something, right? And maybe we apply load here. Oh, not that one. We apply load here. Let me put these things out of the bay. I should have think that. What was it? GH. Okay, let me write it here. HIE. Okay. All right, so sometimes my laptop is finicky. Okay, let's say we have external load here, whatever the number is. Let's say, well, maybe you have another load over there. Maybe I should also, yeah, let's say you have another load there. Let me do it correctly. In a moment, you realize what I don't want these things to be on the way. So this is F. Okay. Okay, we got it. So let's say we have external load here, and this one is like a F, which is a tensional load at E. And then maybe let's say we have a compressive load here, right? Over there. Let's say we have this configuration, and maybe also we have something on the top here. That's another load. And let's say each of them has a value. Let's say this one is 100 kilonewton. This one is maybe 50 kilonewton, 20 kilonewton, and maybe 10 kilonewton. Just some random numbers, okay? So in this truss, there are some members that they don't do anything for us. They are like sitting there free, relax. And we call those members zero force members, like they are idle. And they are neither under compression nor tension. So let's analyze joint H together. And in a moment, you realize what do I mean exactly. Or maybe G, the easier one, like joint G, okay? Let's draw the free body diagram for this joint. So, so you could follow, let's say this line, I just draw it outside, so not to make the image too messy. Let's say that's that line and that's this line. And let's say this is this joint. Okay. And in a moment, you realize what I'm planning to do. So this is G, like point G. I just draw it outside so the image doesn't get messy, because it can get messy soon. So if I draw the free body diagram only for this point, for this joint G, right? So I know that GH is a two-force member, and a two-force member apply load in the line of action GH. And I know GI is a two-force member, and I know GC is a two-force member. And again, you see, I assume that all these members, they are under tension. They try to pull this point G. Remember the two-force member from previous topic, previous lecture? They apply load along the link, along the line of action on the link. So this force is GI, this one is GH, and this one is CG, all right? So remember, for simplicity, instead of writing FGI, we just write down GI. And by GI, we mean the force in GI. Okay. So in this diagram, we know that we are in a static. We know that this point G must be balanced, right? So if this point G must be balanced, immediately we can say, well, this CG then must be equal to GI, right? There is no way this CG must be equal to GI. Otherwise, this pin start walking up or down, right? But there is nothing for GH here to be canceled. But we know we are in a static. And if GH has a force, if it has a number, let's say even a small force, 1 Newton, then this point G start walking to the right, right? And this is not a static. This is not something that we want. So we don't have any choice but saying that this GH must be 0, okay? And if GH is 0, then it means it doesn't do anything. It doesn't have any force. It's basically, it is invisible. I can imagine that there is no GH there and nothing bad is going to happen. I can just remove GH and pretend that I have just air over there. Okay, let's just imagine that we remove GH because we said, well, this GH is useless, the force is 0. And now let's look at these joint H together. All right. I hope you guys are following. If you don't, please stop me. But soon you will realize that what we are looking after here. So I'm just drawing H here for you. This is point H. And so point H, this is one line, right? This is this line. And this is the horizontal line. So let's draw the forces for this H as well. And this one also is a vertical line that we have. Okay, what do we have for point H? Okay, we assume that GH is gone. We don't have that one. So we have HB here then. We have HC. And we have HI here. So this guy then is HB. By HB, I mean the force in HB. This one is HI, and this guy is CH. Okay, with the same concept that we discussed here, right? This CH has to be canceled by HB. So this CH must be equal to HB because we are in a static, everything has to be in equilibrium. And there is nothing to cancel this HI. So this HI must be equal to 0. Okay. So again, another useless member here. It doesn't do anything. It just there, but the force is 0. So far, you guys are following? Okay, I take it as a yes, right? We just look at G here. We look at H here. That's it. But if we continue with joint I, do we get the same things? Let's try it. I. So not that one. So this is a horizontal line. I'm just drawing the, basically the joint I, right? So joint I, what do we have? So before we forget, this one was joint G, we analyzed. This one was joint H, we analyzed. And this one is joint I. We'd better be organized here, otherwise soon things get very messy and then we confuse where we are. Okay. So the forces that I have here, what do I have here? Well, I have this load coming from BI. I have this IE. I have these basically GI. We just found that this HI is useless, so we took our wrench and we just remove it. We don't need it. If it is 0, if it doesn't do anything for us, then why should we keep it there, right? And then we have this 50 kilonewton applying there. So let's see what we have here. BI, EI, and GI. So now I have an external load here. When I have an external load, it means this GI, there is something to cancel it, right? If I find the component of this load along this line, then it means I found GI, okay? And also in this scenario, BI is not equal to EI. Why? Because this GI is gonna be there doing something for us. So let me clarify that point because it's important. Again, I've seen a student make mistake. So if I find the component of this guy, this GI, right? Let's say this GI. This GI has component. So it's going to be one component. That's another component. If this angle is alpha, this one is GI sine alpha, and this one is GI cosine alpha, right? And this, so we have the forces in X and Y. We have the forces, we call this one X, and we call this direction Y. So if you write the relation, and I want you guys to try it later, if you write the relation for sum of the force in X equal to 0, remember we are in a static, even for this pin, for this joint I that we are analyzing. The same with other joints, the forces must be balanced. So sum of the force in X, sum of the force in Y equal to 0. So we don't care about moment because all the forces are passing through one point, right? There is no moment basically. If you write these two relations, you realize now that GI cannot be 0 and BI is not equal to EI, right? So it means GI, we have to keep it, it's not useless. All right, so probably by now you realize that if you look around this truss, probably we are going to have similar story for DF. Why? Because if you look at this D member, right, you see there is no load on this pin. So then this FD is free. It doesn't do anything for us. So that's another force member then. FD is 0. Okay, these members, they are called zero force members. It means if you take them out, nothing bad is going to happen to this structure. It's not going to fail because they are zero force member. Now the main question is, well, if they are 0, if they are useless, then what's the point putting them there? Because it makes our structure more expensive, and also it makes it heavier. What's then the point of adding them to a truss? Any idea?
Is it for redundancy? Sorry.
Go ahead, Oliver, first.
Okay, I was just saying for redundancy, probably.
For redundancy, but if they are redundant, then what's the point? We just remove them.
Or I guess maybe for deformable bodies, then they wouldn't actually be 0 force members.
Okay, that's a very good point. Yeah. Yeah, go ahead.
So like right now we have external forces acting on it. So if the forces change, like wind or whatever, tree falls on it, we might need those members.
Exactly, yeah. Thank you, Emily. So both answers were correct. So as Emily pointed out, we need these 0 force members because right now on paper, they are 0. But in practice, you never know. Maybe wind is coming, right? Or maybe one day you're passing over a bridge and you try to hang yourself from, not you, somebody tried to hang himself from a point. So they apply a load at point H. Wind is coming, or maybe there are other forces, right? And so we need to have them in case there are other forces. Otherwise, everything on paper is stable, but in practice, even a small wind, everything is going to fall down. Another reason that Oliver mentioned is because in practice, we are dealing with the flexible bodies, right? Remember in this course, we said things are flexible, they are not rigid, and they can deform. If they deform, it means now the geometry is not as we expected on the paper, right? On a paper, the geometry, everything is aligned and is perfect. But when you build these things, and let's say on this bridge, a truck is passing, things can deform and the shape of things can change. So basically in this point G that you can see here, these CG and GI now they are not in one line. So you cannot simply say that they cancel out each other, all right? So We need to have 0 force members in a truss. That's essential for a design. And in fact, design of a truss by itself is an art. How to optimize it. By optimization, I mean to have the smallest amount of material, less weight, and more strength. But you need to also consider the 0 force members for future loads. All right, so, but for us in MEC 260, before we solve a problem, a truss problem, we need to find all these 0 force member, cross them, and draw another truss which is simpler and easier. Then we start solving the problem. Okay, so again, in truss problem, before you do anything, get rid of all the 0 force members and then start solving the truss problem. But how do we get rid of force members? Do we need to do all this analysis? No, it was just to show you why these are 0. So a truss 0 force member can be easily identified. If you look at a joint, like this one, for example, let's say this joint, G to start, right? So you see 2 members are in one line, 2 members in one line. Another member is, it has an angle with them. It can be perpendicular or any angle, and there is no external loads. So 3 conditions then. Let me write them down here for you. So 3 members connected, 3 members connected, okay? If there are 4, it's not forget it, there's not gonna be any 0 force members. So 3 members, first of all, 2 of them in one line or collinear. And then the third condition, no load on the joint. All right, so look at D. D has these 3 conditions, 1, 2, 3 members. Good. Then we have 2 of them in one line. They are collinear. We are happy. There is no external loads. Then get rid of DF. Oh, you may say, what about F? You say, okay, just look at one joint, one point. If one point has these 3 conditions, you are good to go. Remove DF. What about FE? So imagine that DF is invisible, it's not there. So we say 1, 2, 3 members, that's the first condition, that's good. 2 members in one line, we are happy, that's good. But wait, there is an external load. So we stop there. There is no force member here. Over here, G, it has our condition, we remove GH. After we remove GH, we realize that HI has the condition that we want, right? Then we remove HI. But over here, we stop at I, okay? So as simple as that. You start with each individual joint. You imagine that that's, if it is a 0 force member, that's invisible, and then you continue. Okay. Now, with this long introduction, let's solve one example together. So I let you guys to read this one and see how we can approach it. So let's see what we have. We have a truss, it's large, it's 2 meters each of the members. And the question asks to find forces in each member of this truss. And for this problem, I want to use the method of joint. Later, you will learn the method of section, which you can solve it with the method of section yourself. So first step in method of joint is to find the reaction, okay? We start with free body diagrams. So A is a pin connection. So if A is a pin connection, then it's gonna have AX and AY. And this guy D is a roller, just one connection. So we use the formula that we know. So we call this one then AX, AY, and we call this one D. I don't write FD, just D, so you realize, right? So it's simple. You use the formula that you know. So immediately you realize that AX must be 0, right? Because you don't have any force in X. AY 600 Newton and D 300 Newton. I guess that's easy. You can do that like this one. If you take the moment about D, you can get that one, and this one, if you write down that sum of the force in Y equal to 0 gives you that, and this one, sum of the force in X equal to 0. So that's the first step. The second step is, there is only second step, is just look at each joint, but wait, before that, we need to find out if there is any zero force member. Tell me, is there any zero force member? Remember the 3 conditions? See if you can find any. Any idea? Do we have a zero force member?
Is the one going from E to C a zero force member?
Yeah, exactly. Yep, thank you, Oliver. So C is zero force member. Why? Look at joint C. It has 3 conditions that we want, like 3 members, 2 of them in one line. There is no external load. So C is 0. We need that one because later for next steps that we solve, we know that that one is 0. We don't need to do anything about it. So how we approach this problem? Very, very simple. We start with joint A, and we continue our solution all the way. We draw the free body diagram for one of the joint that we like, but we prefer to start with a joint that has the basically the minimum number of unknown. So let me draw joint A here for you. So I start with and joint A. Okay. So for each joint, we carefully draw the forces. So let's say this is X and this is Y. So first, if we have external load, which we do, we have this guy AY here, which we just found this AY, how much? 600. So this is 600 Newton. So what else? This joint A, there are 2 members that has been connected to this guy, right? So one is AB and one is AF. And remember our assumption? We said that we assume all the forces, they are basically tension. And when we say tension, it means they are basically pulling that point, pulling that joint to other side. Like this AB try to pull joint A, and this AF also the same, try to pull it, right? They're all tensional load. So then we call this one AB, and we call this one AF. Okay, so that's our free body diagrams. From geometry, I can see this one is 45 degree. So then this angle is 45 degree. Then simply we try to find out the component of the load. So let's say this AF has 2 components in X and in Y direction. So this component and the other one. So, and this guy has to be AF sine 45. And this one has to be AF cosine 45, right? So that's my free body diagrams. And the only tools that I have, I'm just continue writing over here. only tools that I have is sum of the force in X equal to 0, sum of the force in Y equal to 0. Here for trusses, we don't need the moment. Why? Because for one pin, the moment is 0. All the forces are passing through one point. So the forces in X, what do I have in X? I have AB. Remember, it is in X direction, it's positive, plus AF cosine 45 equal to 0. What about sigma Fy? What do I have? I have AF sine 45. Again, it is positive. It's going up, plus 600, right? It's also positive going up. Remember, our X and Y direction equal to 0. So from here, simply, I can find AF minus 600. Let me write it down over there. So I have more room there then. So from here, I can find AF minus 600 square root of 2. So that's AF. If I substitute AF in the first equation, let me move myself up there. And from this guy, I will get AB. If I substitute there, it's going to be 600. Okay, so far we found two members, one AF and one is AB. So we found a negative number here. What does that mean? It means simply that this AF is under compression. This is positive, this one. This is under tension. But in your exam or in your assignment, you don't need to write the positive and negative sign. Implies that if they are under tension or compression. You don't need to change anything. You just leave it as it is, and that's it. So that's joint A. Let me solve another joint, and then we'll see if you guys have any questions. So joint F. So we just find our way from A to F, and then next and next, from left to right or right to left. It's up to you. So let me draw joint F here. Let me draw it bigger. This is joint F. Let's say this is X direction, and this guy is Y direction. Oh, I cannot draw it correctly. Okay, this is better, Y direction. All right, so this is X and this is Y. Remember, this is positive, this one is positive. Okay, so let's see what we have in this joint. In this joint, we have AF. Always again, we draw them positive, right? Coming out of the pin. They are trying to pull the pin out. BF, maybe let's try it smaller like this one, doesn't matter. And this one, EF. Okay, so joint F, it has 3 members, and we draw the 3 members there. All right, so let me write them down, the name. So this one is EF, this one is BF, and this guy is AF. All right, so we simply find the basically the component of this load, AF. If we do so, then we ended up with this guy and this guy. This one is AF cosine 45, the angle is 45, and this one is AF sine 45. As you can see, guys, it's really boring, right? It doesn't have anything. It just, we draw for each pins, and then we simply write down the sigma fx and sigma fy. Let me continue on second page here. So for joint F. It was joint F, right? Yeah. So sum of the forces in X equal to 0. What do we have in X? We have EF. We have minus AF cosine 45. Be careful about the sign, right? About the direction. So this one is the opposite direction of X. That's different than this plus minus one that we have here. That's the different things. So in X, we have EF, we have AF cosine 45 equal to 0. I don't know EF, but we just found AF. What was AF? Don't forget this minus sign. Minus 600 square root of 2. And then we have cosine 45 equal to 0. It gives me EF, what is going to be negative 600 Newton, right? That's another member which is under compression. And yeah, similarly, you write down some of the forces in Y equal to 0. Remember, we're looking at this image. So in Y direction, what do we have? We have BF, we have AF sine 45 equal to 0, and minus BF minus 600 square root of 2 sine 45 equal to 0 gives me BF equal to positive 600 Newton. All right. So, and then the rest, which I let you guys to continue for example, joint B. Draw the diagram later for joint B and find out the rest, right? So as you can realize, this method is really boring. It's really slow. And imagine that you have truss that has 100 members. So it means you have like 100 joint that you need to solve, right? Imagine your job as an engineer in a firm is that somebody in the first day gives you a truss with 2,000 force members. And they said, okay, your task is for the next 6 months to find the forces in this truss. You say, really? But this is the way it is, right? So please continue for joint B later, because I'm getting sleepy really here. But later I'll put this one for joint B. Okay, let's then move to the next method. Maybe next method can help us a little bit more. So I let you guys to read this one. So I'll do the same, I'll read it. So basically in this truss, we just interested in one member, BC. We don't care about the rest because the question says that it failed at BC and we want to know the factor of safety in this member. To find the factor of safety, we need to find its force, right? So how can we find the forces in BC? Well, one method is the previous method of joint. It means we have to start from joint D and until we get to B, which is boring, right? And oh, by the way, we have to also find the reaction at A and H. But there is a better way. When we are dealing with a problem that, unlike the previous one, the question asked us to find only one force member. We don't go to method of joint. We use the method of section. How does it work? As the name implies, you section the truss to two, you cut it to 2 parts. Like here, the left part and the right part. You are allowed only to cut 3 members, right? So for example, you cannot say, oh, well, I like to cut it like that one. It means 1, 2, 3, 4, 5. No, it's not something that we want. And in a moment, you'll see why only 3. You may cut it like that one, 1, 2, 3, that's okay. Yeah, it's acceptable. Okay, only 3 force members. That's the first rule. The second rule is, well, of course we are interested in BC. If we are interested in BC, then when we cut it, this section has to include BC. Like this one is useless, right? We don't care about this one if we section it. So our section must include the member that we are looking after, like this BC here. So that's the first step. Now that you section it, imagine that you cut it from these 3 members and you just keep one side and throw out the rest. Like this one, I just imagine that the left side, I just throw it out. It's invisible, it's not there. What I can see here is only this right section. So sorry, I removed the left section and only I left with the right part. So for a moment, I missed my left and right. So let me draw it again quickly here. So this is what I have. This is the E. This is this guy. And this is that one. And that one. Yep. This is shorter. This guy is not that. This one also is shorter, right? Because we cut it, and also we have another member over there. This is what we have. Do you agree, guys? So this is joint, this one is joint, joint, joint. Yeah. And oh, we have only 4 minutes. Sorry, guys, this today got a little longer, but I promise you in 5 or 6 minutes we will be done. So this is C, this is D, this is E, and this is F, right? So remember the rest, they are not there. We remove them. They are gone. They are invisible, right? So they are like this. And the rest, what we don't care. So then the next step, we put the external load, whatever we see on this section. So I have only one force here, 10 kilonewton there. So I put it there. Have 10 kilonewton, no other external load, and that's it. So the members that I cut, they apply some loads to this joint, like this BC, it apply load to this joint C. I draw it like that one. The same for BF, and the same for GF, okay? And again, I assume all the loads are tension. It means they are pulling out those pins. So this is BC, this is BF, and this is GF. One more time. After we cut these truss, we draw only the portion that left, and it's up to us. You can keep the right side or the left side. I prefer to keep the right side because the left side involves these supports, and it means extra work for me, which I don't like to do. So, and then the next step, the members that I cut, I just draw their forces. We know they are 2 force members, and we know that they apply load at this joint C, F, and F each, and the loads, we assume they are tension. So this is in fact our free body diagrams, and this is something that we have to use. And in fact, that's the only things that we have that we need to use to basically find the BC that we are interested. So any idea how we can continue? If it is our free body diagram, how we can find BC? Maybe you guys are tired, but remember, always in a static, we have these 3 tools: sum of the force in X, sum of the force in Y, and sum of the moment in about any point is equal to 0. This is our only tools, or our only equation in a static. Okay, here maybe I prefer to use this guy, the take the moment. Let's try and see if it can help us. I take the moment about any point that I want, which if I look closely, I prefer to take moment about point F. And you can see why, because if I take the moment about point F, it means I'm getting rid of this GF and BF that I'm not interested. So I only left with what? With BC multiplied by its distance, which is 2.5 meters. And it tried to rotate everything about point F counterclockwise, so it is positive then. And then I have this 10 kilonewton, which is counterclockwise multiplied by the distance, which is 2 meters, equal to 0. From here, I can find force in BC. So which is 200 divided by 2.5, 20. And it gives me 8 kilonewton, right? So we are almost done, guys. So if you guys could wait for another 3 minutes, we are done. So we found the load in BC, right? By just simply taking a moment about point F. And then the rest is what you learn in module 2. If you know the force in BC, then simply you can find, let me write it down here, stress. Stress is force divided by A, like here, 8,000 divided by area. So the question says that the diameter is 10 millimeters, pi r squared. It gives me approximately 100 megapascal. And we know the factor of safety. Factor of safety, it is equal to SY, the strength divided by stress, right? Here, the strength of material is 120 megapascal. The stress is 100. It is 1.2. So our safety factor is 1.2. So, but the things failed. So you go to your book, and in the catalog, you realize that people in the past who have done tests and designed trusses, they choose a factor of safety of at least 1.5 for trusses. So maybe that's the reason that these things fail. The factor of safety was too small. So as an engineer, you suggest that, well, maybe the diameter of 10 megapascal is not a good idea. Maybe you should use a bigger diameter, and which you can find out if your factor of safety is 1.5, then try to find out the right diameter. Or maybe you say instead of this material, maybe you can use a material with a higher SY, higher strength, all right? So that's method of section. Again, one more time. In method of joint, you start from each individual joint, you draw the free body diagram for each joint, and slowly you find your way to the members that you are interested. Or if you are asked to find all the forces for all the members, the forces for all the members, you have to use method of joint. If there is a problem like example 2, which you are interested in only one members, then you need just to section or cut the truss to 2 halves, left or right, ups and down, doesn't matter. You are allowed to cut only 3 force members, and you have to include that force that you are interested. Then simply you use the equation, sum of the force or sum of the moment about the point equal to 0, and you continue the rest. Sometimes in truss, after like a question like example 2, after we find the force, we calculate the stress to make sure that the truss doesn't fail. This is all we need to know about solving a truss. So I left you with this challenging problem to think about it after the class, but I will post the solution as well for this one, but don't look at my solution, and try to see how you can find the force in GF in this truss only with one section, right? How you should cut it. Should you cut it like that? Should you cut it like that or like that? Try to see if you can find out, all right? That's it, guys, for today. Please check your emails. I'm gonna send you an email and I'm gonna set up an office hour for Monday. That's the day before your exam, probably around noon. I figure it's gonna work for most of you. That's totally optional. If you have question, you can just come by at any time in that 1 hour. Probably if I set it from, let's say, 11 to 12, anytime you can start from the beginning to the end, stay there if you have time. If you don't have question, but still you like to come to the class, listen to your friend's question, that's up to you. And if you don't have the time to attend any of those, I'm gonna record it as well, and I will post that office hour as well, so you can watch it if you are interested. If, let's say, you don't have any question, you just like to listen to your friends. That's it. And these things, the lectures for today and the notes for today, is going to be posted by late evening tonight. All right, guys, good luck. Please study for your exam. If you have questions, send me an email, or if it is related to assignment or sample exams, then your TA is the best to help you. You can use sample exam 1, sample exam 2, or I call them sample midterm 1, sample midterm 2, and the scary exam. These 3, they are on the topic of module 1, 2, and 3 related to what you're gonna be tested next Tuesday. And the exam, by the way, before again I forget, is online. Of course, you know, is on Canvas. It's gonna pop up on the first page. You saw the midterm, you click on it. If right now, if you click, it doesn't show anything. It just tell you that come back next Tuesday. But next Tuesday, the questions are there, similar to assignment. You just write down your solution, you take a photo and upload it. I will give you extra half an hour for uploading, so don't worry about the extra time that you need to spend about uploading. And I'll try to be on Zoom for the last half an hour of that day. So if you run into any problems, then I can answer you. Okay, I guess I talked a lot, so maybe I should leave now. But before I leave, any other question? Because it's getting late, maybe everybody's getting tired. Should you say goodbye?
I have one question from the extra tutorial that you posted yesterday.
Thomas, okay. So,
should I just send an email or?
Yeah, if you could send me an email, that would be the best. Because I see it's getting late, maybe for some students. I can set up an office hour right after that. But let's send me an email. Either I'll set up an office hour, or I just try to answer you by email. Okay?
Sounds like a plan.
All right. All right, guys. Don't yeah. As Thomas mentioned, there is an extra tutorial that I posted yesterday. Try to watch that one if you haven't yet. Okay. All right, guys. Have a good day and bye for now. Goodbye.